All right, let's dive into something that's absolutely critical in the world of industrial engineering. IS 1893, Part 4. You know, this isn't just some dry document. It's basically a survival guide. It's the shield that protects our most vital infrastructure from the chaos of an earthquake. If you're involved with a power plant, a chemical facility, or any of those industrial giants in a seismic zone, this is for you. So let's break it all down. So here's the game plan for our deep dive today. We're going to start with the big picture, the what and the why of the standard. Then we'll get right into the nuts and bolts, how to categorize your structure, how to figure out the forces it's up against, and the different ways you can analyze it. We've even got a special section on those tricky stack-like structures before we wrap it all up with the key takeaways you can actually use. You can't build a strong structure without a solid foundation, and it's the exact same thing with this standard. Before we even look at a single formula, we really need to get our heads around the core philosophy, because that philosophy drives every single decision and every calculation. If you get this part right, honestly, everything else just clicks into place. Now, let's be clear, this standard isn't for your average office building or shopping mall. Part 4 is written specifically for the heavy hitters, the core of our industrial infrastructure. We're talking about the power plants that light up our cities, the factories producing essential materials, and facilities handling things that you really don't want spilling. It's incredibly comprehensive, covering everything from huge steel plants to those really tall, skinny chimneys and silos you see everywhere. Each one has its own unique challenges that a general building code just can't handle. Okay, this right here is where it gets really smart. This is the core design philosophy. The goal isn't just to build an indestructible fortress. It's a much more intelligent, risk-based approach. For those minor, everyday tremors, the facilities shouldn't even blink. Operations just continue as normal. For a more serious event, what we call the design basis earthquake, or DBE, we might see some cracks, some non-structural damage, but the main structure has to remain sound. But for that massive, once-in-a-lifetime quake, the MCE, the mission is simple: life safety above all. The building might be a total loss, but it absolutely cannot collapse. This tiered approach is really the heart of modern seismic design. So let's put some numbers to those terms, DBE and MCE. The design basis earthquake, or DBE, is the event we design for most of the time. It has about a 10% chance of being exceeded in a 50-year window. But then you have the MCE, the maximum considered earthquake. This is a whole other beast. It's much rarer, with only a 2% chance of being exceeded in 50 years. And look at that key detail at the bottom. The code tells us to consider the MCE as having twice the intensity of the DBE. This is a crucial distinction that forms the bedrock of the entire risk-based system we're about to explore. Okay, so we have these two levels of earthquakes, the DBE and the MCE. So how in the world do we know which one our structure needs to be designed for? Well, this is where the standard gets incredibly practical. It all boils down to one simple but critical question. What happens if this thing fails? The answer to that question is going to set you on one of 4 very different design paths. This is the very first decision you have to make, and it is a huge deal. It literally dictates everything that follows. Category 1, that's for the structures where failure is absolutely not an option because the public could be at risk. Think of a containment building for hazardous materials. Category 2 is for things that are critical inside the plant. A failure might not affect the nearby town, but it could start a major fire or shut down the entire facility. Category 3 is for things that are really expensive but not necessarily dangerous, and Category 4 is pretty much the catch-all for everything else. And here you can see what this looks like in the real world. A blast-resistant control building, a chlorine storage tank, no-brainer, Category 1. They have to be designed for the absolute worst-case scenario, the MCE. But what about a fire station or a critical boiler house? Those are Category 2. They need to stay standing so they can be used in an emergency. A simple storage shed, Category 3. Its collapse would be a financial headache, but not a disaster. And the company canteen, that's a classic Category 4. This table really makes those abstract definitions feel tangible. So once we figure out our earthquake load, the EL, we can't just design for that by itself. The structure is also dealing with its own weight, the weight of equipment, and so on. That's where these load combinations come in. This is all about stress testing the design on paper, mixing and matching all the possible loads to find the absolute worst-case scenario. Those numbers like 1.2 and 1.5 are safety factors to account for any uncertainties. But check out that last combination, 0.9 DL plus 1.5 EL. That's a fascinating bit of engineering right there. It simulates a situation where the earthquake is shaking the building upwards, actually reducing its stabilizing self-weight by 10%, at the very same moment the horizontal forces are peaking. It's that kind of clever, worst-case thinking that makes a structure truly safe. All right, let's get to the main event. We've talked philosophy, we've talked categories. Now, how do we actually calculate that EL, the earthquake load itself? This next part has the single most important formula in the entire standard. And here it is, the design horizontal seismic coefficient. This little number tells you what percentage of your building's weight you need to apply as a sideways force to simulate the earthquake. Now, it might look simple, but every single one of those variables, Z, I, R, and SAS, is packed with critical information. We're going to unpack each one because if you can understand this formula, you truly understand the core of IS 1893. First up is Z, the zone factor. This one is pure geography. Where is your structure located? India is mapped into different seismic zones, from II, the least active, to V, the most active. And you can see right away the Z value, which basically represents how hard the ground is expected to shake, jumps up significantly in higher risk zones. A structure in Zone V has to be designed for a base shaking that's over 3.5 times stronger than one in Zone. Next is I, the importance factor. And this is where that categorization we did earlier comes right back into play. This is how we turn risk into a hard number. For a standard Category 4 structure, I is just 1. But for a critical Category 1 structure, it jumps all the way to 2.0. Think about that. For the exact same location and the same building type, the critical one has to be designed for double the seismic force. The code is literally building in a higher factor of safety based on the consequences of failure. Now, R, the response reduction factor, is one of the most brilliant parts of the code. It recognizes that buildings aren't just rigid blocks. Good ones can actually absorb earthquake energy by bending and deforming in a controlled way. We call that ductility. Think of bending a paperclip. It gives without snapping. A very ductile system, like a special moment-resisting frame, gets a high R value of 5.0. Since R is on the bottom of our equation, that reduces the force we have to design for. But here's the catch. It's a promise. When you use an R of 5, you are making a deal with the code that you will provide all the special reinforcement detailing to guarantee that ductility. If you don't, the building won't act like a paperclip. It'll snap like chalk, and that's exactly the kind of catastrophic failure this factor helps us avoid. And our last variable is ZA-G. This is where the physics of the earthquake meets the physics of your specific building. See, every structure has a natural rhythm, a period of vibration, the time it takes to sway back and forth. If that natural period happens to match the rhythm of the earthquake shaking, you get resonance. It's like pushing a kid on a swing at just the right time. They go higher and higher. This SAW-G value, which we pull from charts in the code, tells us how much the ground motion gets amplified for our building's specific period. And it's hugely affected by the soil. Soft, jello-like soils can amplify shaking tremendously, turning a moderate earthquake into a real monster. So, we've put together our formula. We've calculated our design force coefficient, but that's just a number. What do we do with it? Well, the next step is to apply that force to a model of our structure and see what happens. This is where the real engineering starts, and the standard gives us a few different ways to tackle it, depending on how complex and critical the project is. You can see right here how the required level of effort is tied directly to risk. For a simple, low-risk structure, you can get away with a simplified static analysis. But as the risk goes up, either because it's a critical category or it's in a high seismic zone, the code demands more. For any Category 1 structure, no matter where it is, you must perform a detailed dynamic analysis. That means using a more sophisticated tool, like a response spectrum analysis, which checks how the building reacts to a whole range of earthquake frequencies, not just one single force. It's how we make sure our most important facilities get the highest level of scrutiny. Okay, let's switch gears and talk about a special case. Industrial sites are full of these tall, skinny structures, things like chimneys, silos, big refinery columns. During an earthquake, they behave very differently from a normal building, so the code gives them their own special section with their own rules. So what is it that makes them so different? Well, in engineering terms, they act like giant cantilevers. Imagine a diving board fixed at one end. When the ground shakes, you get this whipping effect, where the very top of the structure moves way more violently than the base. This can create absolutely incredible forces at the top, so the standard has a very specific way of dealing with them. And it all starts with getting the time period right. Because their behavior is so predictable, the code gives us the specific, more accurate formula just for them. Getting this time period T calculated correctly is the critical first step. Why? Because as we just saw, T is the key you need to unlock the right SAW/G value from those response spectrum charts. A small mistake here could cause you to seriously underestimate the forces on your structure. Now, to use that formula, we need the CT coefficient. And this table shows us exactly where it comes from. It's based on the slenderness ratio of the structure, which is really just a fancy way of saying how tall and skinny it is. You can see that as the stat gets more and more slender, that CT value goes up, which means it will have a longer natural period. It's a really direct way of accounting for the unique shape of these structures. And here it is. This is one of the most critical safety rules in the entire standard, buried in Clause 12.2. Any vertical part that sticks up, like a chimney on a roof, must be designed for 5 times the normal horizontal acceleration. 5 times. This is to account for that massive whipping effect amplification we talked about. And this doesn't just apply to the chimney itself, but also, crucially, to the connection that holds it to the main structure. A failure at that connection isn't gradual, it's sudden and catastrophic. This rule is there to make sure that doesn't happen. Whew, we have covered a ton of detail, from high-level thinking all the way down to specific formulas. So let's just take a step back and pull it all together. What are the key things you really need to remember when you're working with this standard? If you take away anything from our chat today, let it be these points. First, get the category right. It is the single most important decision you'll make. Second, understand the story that the main formula tells. It's about location, risk, and the promise of ductility. Third, respect the special cases, especially that 5x rule for projections. Fourth, remember that a brilliant design on paper means nothing without proper construction. That ductility you promised with your R factor, it has to be built, on-site with careful detailing. And finally, never, ever forget about the ground your structure is sitting on. And that brings me to one last thought. This standard is an incredible tool for ensuring a baseline level of safety, but the code itself encourages us to go further, especially for important projects. So the question I want to leave you with is this. How can we move beyond just checking the boxes for compliance? How can we start using detailed site-specific data to build industrial facilities that aren't just safe, but are genuinely resilient for whatever the future might throw at them?